So this is the fourth section of the Conic Sections 2 chapter, and here we're looking at tangents and normals to an ellipse. So we know that the equation of an ellipse is x squared over a squared plus y squared over b squared is 1. So that's in Cartesian form, and parametric form it's going to be x equals a cos t, y equals b sine t, and actually we're going to use this to help us derive the formula that gives us either the equation of a tangent or the equation of a normal. So let's go through what these are. We will be proving at least one of these in a moment. I think the equation of a normal will do. So for a tangent, the general form of its equation is going to be bx cos t plus ay sine t equals ab. And then for a normal, a bit more of a mouthful, the normal's a bit more to it. That's going to be ax sine t minus by cos t equals, in brackets, a squared minus b squared cos t sine t. So we want to find the equation of the tangent to the ellipse with this equation at this point here. Now we have two different ways of doing this question. We could do either parametric differentiation or implicit. Let's do both, so you can compare and contrast and decide which way you would prefer to do it. So parametric over here, implicit over here. So doing it the parametric way, we've got x equals 3 cos t, which means that dx dt is going to be minus 3 sine t, and y equals 2 sine t. So dy dt is going to be 2 cos t. So dy dx is dy dt, so 2 cos t over dx dt, which is minus 3 sine t. Okay, so we've now got our m, and we'll use y minus y1 equals m x minus x1. So that's going to be y minus y1, so 2 sine t, equals m, so that is minus 2 cos t over 3 sine t, x minus x1, so that's x minus x1 is 3 cos t. Okay, now to get rid of this nasty denominator, probably before we expand the brackets, let's multiply both sides by 3 sine t. So we'll have 3y sine t minus 6 sine squared t equals minus 2 cos t, then times by this bracket x minus 3 cos t. We'll expand the brackets, so we'll have 3y sine t. Now I'm going to move the sine squared t across. Oh no, I'll do that afterwards. You'll see why in a minute. Equals minus 2x cos t, and then plus 6 cos squared t Now the reason I said I was going to move that sine squared t across, you can probably see why. Sine squared plus cos squared is 1. So if I move the sine squared t over here and put it with a cos squared t, I'll actually just end up with 6. So let's do that. So I've got 3y sine t equals minus 2x cos t plus 6. And then I could just add the 2x cos t to both sides to get this. Now, you don't have to go through all of that. You've basically got your answer for the equation of a line of a tangent here. The question doesn't say leave it in a particular form. If it did, then you probably might do something like this. If it said leave it in the form, I don't know, a sine b plus bx sine t equals c, then you'd go to this to find a, b and c. But here, this is the equation here. That's fine, yeah? So only go through this process here. I mean, you know, if I was doing it, I'd probably go to at least this step, expand the brackets, probably at least do that, or go to here. Yeah, but unless the question asks you to do it, it's not necessary to rearrange and expand, because the equation of a line is here. That's the equation of a line, isn't it? And that's what we've done here. Right, so let's try the same question using implicit differentiation. So probably want to get rid of the denominators of 9 and 4. So we'll start by multiplying everything by 36, I think it's going to be. So we'll have 4x squared plus 9y squared equals 36. And then with the implicit differentiation, the 4x squared will become 8x. The 9y will become, or 9y squared will become 18y dy dx. We're differentiating a y term if it was an x, and then the 36 becomes 0. So we just need to rearrange it to make dy dx the subject. So we'll have dy dx equals, so I will have negative 8x divided by 18y, which I suppose I could simplify. If I divided both of those by 2, I'd get negative 9, not 9, 9 will be at the bottom. So negative 4x over 9y, so that's my gradient function. Okay, so I'll now want to find out, let's just write down up here that we've got our dy dx. So dy dx equals negative 4x over 9y. We want to find the gradient at this point P. Okay, so at P, dy dx becomes minus 4x. So minus 4 times by x, which is 3 cos t. So notice this way, implicit, you need the x and the y coordinate, and then 9 times by 2 sine t. So that will give me something like negative 12 cos t over 18 sine t, which simplifies to minus, divided by 6, got a bit confused there, divided by 6, so minus 2 cos t over 3 sine t. So this is exactly the same value for m as we got before, so I don't need to carry on from here. I will just do maybe a line showing you the same value of dy dx we got by using parametric. So whether you do parametric or implicit is up to you. I probably think the parametric is probably slightly quicker than the implicit way to find the gradient. Okay, so here it says show that the equation of the normal, so we mustn't forget to do our -1/m to the ellipse with the equation here, okay, and this point at that point, and its equation is given by this, so this is what we want to finish with. Now, like the previous question, we could, if we wanted, use implicit differentiation here or parametric here. Now, if we look at the answer has sine t's and cos t's in it, which is a clue to tell us we should really be using the parametric, because the parametric is going to give us sine and cos. If I use the Cartesian equation here and do implicit differentiation, I'm going to have an expression in terms of x and y, and then I'm going to have to substitute back x and y for this. It creates extra work. So by looking at the answer, the clue is use the parametric differentiation. So x equals a cos t, so dx dt is going to be minus a sine t, y is b sine t, so dy dt is going to be b cos t, so dy dx will be dy dt, so b cos t over minus a sine t. Now we want the gradient of the normal, which means we need to flip this one and change its sign, a negative reciprocal. So the gradient of the normal is going to be, so I put normal gradient here. So we get rid of the minus sign and it will just be a sine t over b cos t. So now we're going to use y minus y1 equals m times by x minus x1, which is a cos t. So from here we're going to multiply everything through by b cos t to get rid of the fraction. So I'll just put times b cos t here. So we'll have b y cos t minus b squared cos t sine t equals, I'm going to have to go into another line down here, a sine t times by x minus a cos t. So the next step now would be to expand those brackets on the right hand side. So by cos t minus b squared cos t sine t equals ax sine t, so just expanding the brackets on the right there, minus a squared cos t sine t. Now I've got two terms that I've got sine t cos t in, so I'm going to bring those to the same side so I can factorize them, and then move the ax sine t to this side, and I think then that's the final step. So ax sine t actually be minus ax sine t, so I'm probably going to be multiplying by -1 at some point, plus by cos t equals to b squared, now let's factorize it, b squared minus a squared cos t sine t, and then what I'm going to do is times everything by -1, and that will put it in the correct format. So that will now give me the ax sine t minus by cos t equals, now if I multiply the bracket by -1, the terms effectively swap over and we get the result as required. Okay, so it's just a point P. Now we're given an actual point this time rather than a general point. Lies on the ellipse, okay, with this parametric equation. So we're using the parametric form. Find the value of theta at the point P. Right, so let's make a start then on part A. So if we know that x is 2 and x is 4 cos theta, so we've got 4 cos theta equals 2, which means that cos theta equals a half. Now if we solve this for theta, remember there are multiple solutions. Our calculator is only going to give us the first one, so we might even use a cast diagram to help us. So if I do the cos inverse of a half, now remember we are in radians for this, we get a third pi, or pi over 3. Okay, so let's do a little tiny cast diagram here. So pi over 3 is going to be here, like this is my pi over 3, little tiny pi over 3 there. And so CAST, since we are doing cos, then the other value of cos that's also positive is going to be down here, which is like 2 pi minus pi over 3, and 2 pi minus pi over 3, it's like 6 pi over 3 minus pi over 3, so it's going to be 5 pi over 3. We don't need to go any further because remember theta is restricted between 0 and 2 pi. Then the other piece of information we've got is 3 sine theta equals 3 root 3 over 2, which means that sine theta is going to equal 3 root 3 over 2 divided by 3, which I think is just root 3 over 2. So like before, we will work out what theta is, so we'll do the sine inverse of root 3 over 2, and that also gives us pi over 3. Now, is that the solution or not? Well, let's have a look. Using our cast diagram, the other place where sine theta would be root 3 over 2 would be over here, which is the same as pi minus pi over 3, which is like 3 pi over 3 minus a pi over 3. So it'll be 2 pi over 3. Okay, so we can see that theta must be pi over 3. That's the only one that agrees with both. So our answer would be that theta equals pi over 3. But we must go through this process, checking with a cast diagram or whatever method you want to use to check that we have agreement in both of these angles here. Okay, part B, some new information. The normal to the ellipse at P cuts the x-axis at point A. Find the coordinates of point A. So we're going to start by finding the gradient at A. So that means parametric differentiation. So x equals 4 cos theta. So the theta this time is going to be minus 4 sine theta, and y equals 3 sine theta So dy d theta is going to be 3 cos theta. So then dy dx is going to be dy d theta over dx d theta. Because we want the gradient at the normal, we want the negative reciprocal of that. So then we will have 4 sine theta over 3 cos theta. So this will be the gradient of the normal. Now we can substitute in our value of theta. So what we had there wasn't the gradient, it's the gradient function. So we'll substitute in our value of theta to work out what the actual value of the gradient is. Now that we've done the negative reciprocal, so work this out and see what we get. And on my calculator I get 4 root 3 over 3. So now I can use y minus y1 equals mx minus x1, because I want to find the equation of the line. And then once I've found the equation of the line, if I want to find where it crosses the x-axis, that means I'm going to make y equal to 0, but I need the equation of the line first. So y minus y1, so that's 3 root 3 over 2, equals m, which is 4 root 3 over 3, x minus x1, which is going to be 2. So basically this is the equation of my normal. I don't need to rearrange it into any other form. All I need to do now is just substitute in y equals 0, because at y equals 0 is where it's going to be crossing the x-axis. So there's no point rearranging it. I need to just put y equal to 0. So if I put y equal to 0, I'll get negative 3 root 3 over 2 equals 4 root 3 over 3 x minus 2. So it's just about rearranging this to find x now, isn't it? So x is going to equal what's going to be minus 3 root 3 over 2 divided by 4 root 3 over 3, and then add 2 to that, yeah, to find the value of x. And then when I've got the value of x, I can then write the full coordinates. So let's work this out on our calculator, see what we get. That gives x equals 7 over 8. Just quickly did that on my calculator, paused it, did it on my calculator. So now I can write the final answer as a coordinate, so 7 over 8, y is 0, so 7 over 8, 0 as my final coordinate for that. So let's just highlight those answers before we move on to the next example. Right, we need to show that the condition for y equals mx to be a tangent to this ellipse here is this. Okay, now this question basically is all about discriminants. So what we know is that if a line and a curve meet at a single point, that means it's a tangent. And if it's a tangent, that means when we solve, or if they meet at one point, if we solve the equations, or we put the two equations together, we'll end up with a quadratic that's only got one solution, which means that the discriminant is 0. So if they meet at a single point, it means that when we combine the equations, that quadratic that we get has only got one solution, which means that that quadratic that we get, b squared minus 4ac equals 0. So that's what we're going to do. Combine the equations, rearrange it so we get a quadratic, work out b squared minus 4ac equal to 0, and then we should get this expression up here. So let's start by combining them. Now, since the first equation's got y equals mx plus c, that means that I can simply take the mx plus c and slot it in where y is there. So that's going to be my first step. So x squared over a squared plus mx plus c squared, so there's a substitution, over b squared equals 1. Now, to get rid of the denominators, I'm going to multiply both sides by a squared and by b squared. So I will have b squared x squared plus a squared mx plus c squared equals a squared b squared. The next step is going to be multiplying out the brackets. So I'll have b squared x squared plus a squared times by mx plus c all squared. So that's going to be m squared x squared plus 2 lots of mcx. Now I'm going to write it that way around. Normally you'd write them in alphabetical order, but I don't want to confuse it for centimeters, because I've done these questions before and then you think, why have I written centimeters down? So just writing it that way around will just remind me that I'm not writing a unit of length down. Yeah, so 2mcx plus c squared equals a squared b squared. So then multiply those other brackets and we'll get b squared x squared plus a squared m squared x squared. So they look like my coefficients of the x squared. Let's see what else we get. Plus 2a squared mcx plus a squared c squared, and then I'll move the a squared b squared over like this, so I can see my coefficient. So now phi of my x squared, so using this b squared minus 4ac equals 0, a is going to be the coefficient of x squared. Now that's b squared and a squared m squared. Okay, so that's that and that. They're the coefficients of the x squared. The coefficient of x, that's going to be my b, is just 2a squared mc, and c, the number, is going to be a squared c squared minus a squared b squared. So now we can do the b squared minus 4ac. So b squared is going to be 2a squared mc all squared, b squared minus 4 times by a. A is going to be b squared plus a squared m squared times by c, which is a squared c squared minus a squared b squared. A squared b squared. That's going to equal 0. Now I can actually factorize out an a squared here and here. So I'm going to show you what that looks like. So when I square out these brackets, I'll actually get 4 a squared a to the power 4 m squared c squared minus, and then I could write this as 4a squared, taking out a factor of the a squared from the second bracket. So that's just becomes c squared minus b squared equals 0. I can divide through now by a squared, so they cancel out. So that will just leave me with 4a squared m squared c squared minus 4. And what I'll do, I'll expand the brackets as well. So I'll have 4 b squared c squared minus 4b to the power 4 plus a squared m squared c squared minus a squared b squared m squared equals 0. Now I can divide both sides by 4 as well. I could have divided by the 4 before actually, so I can get rid of those. And what I want to do now, if I look at the expression I want to get, it's got c squared on that side. So I'm going to move all the c terms to the right hand side and gather all of the c terms together. Now I've got this is going to be a c term. Let's use the highlighter. So there's a c term there, and there's a c term here and here. So I'm going to put those all together on one side. Now I've also noticed that these are going to cancel out, this a squared m squared c squared, because I'm going to be subtracting a squared m squared c squared. So actually that's going to cancel out, so let's cross that out as well. That goes. So we're still going to carry on by putting the c terms together. So what I'm going to have left is b to the power 4, because I've realised I shouldn't have written a 4 here. That 4 shouldn't be there, because that was just minus b to the power 4. So let's take that out. I hope that didn't alarm you. So that should just be minus that. Okay, so I'll get b to the 4. What else am I going to get? Okay, this will become plus a squared b squared m squared. So plus a squared b squared m squared equals, so the only c term that I've got is going to be this b squared c squared, which is negative on here, over the other side will become b squared c squared, and then I can divide everything by b squared and get b squared plus a squared m squared equals c squared as required. So that there's a little bit of well, not a little bit, but a lot of algebraic manipulations. It's easy to make mistakes, just like I did, put a 4 in when it wasn't needed. So you've really got to take care when working through questions like this. Okay, this ellipse is given by this equation here. Okay, so we can easily find the values of a and b. The line L is a normal to the ellipse at P. Okay, so there's a tangent here like that, and that's a normal to it at that point P, and passes through the point Q where C cuts the y-axis. Okay, so if it cuts the y-axis, that's where x is 0. Find the exact coordinates of point R where it cuts the x-axis. Okay, so here, this is where we're going to be making y equal to 0. Now, to save time, we can just use the equation of a normal, which I showed you on the first slide, the equation of a normal to an ellipse. So our ellipse needs to be in this form, x squared over a squared plus y squared over b squared is equal to 1, where a general point on the curve is given as a cos t, comma b sin t. And if this is the case, then the equation of a normal is given as this: ax sin t minus by cos t equals a squared minus b squared cos t sine t. So that result can just be quoted and used. Now it's not in the formula book, so if you're going to quote it and use it, you would need to memorize it. So the first thing we're going to do is write down the values of a and b. So a would be 5, b would be 3. These can be slotted straight into the formula for the normal, so equation of normal. If you've memorized it, you can use it. If you haven't, then you would have to differentiate parametrically to find the gradient, and once you've got the gradient, use y minus y1 equals mx minus x1, and actually that won't take too long, should only take a couple of minutes to do that. But yeah, putting these numbers in, got the equation of normal as ax, so 5x sine t, minus by, so 3y cos t, equals a squared minus b squared, so that's going to be 25 minus 9, if I'm right, which is 16, so 16 cos t sine t. Now what we need to do is to find a value of t for this specific line, so we need a point that it passes through, and we can use this here. It says it cuts the y-axis as shown. Now it cuts it at q. Now that is the coordinate at the top of the ellipse. Remember that coordinate there is b, and b is 3. Okay, so this coordinate here is 0, 3. So we've got a point that it passes through. So we're going to substitute in 0 and 3 to find the value of t for this line. And then once we've got that, we can then use it to work out any point on the line, and we're going to find that point r. Right, so let's substitute in 0 and 3. So we'll have 5 times 0 times sine t, minus 3 times by 3 cos t, equals 16 cos t sine t. So obviously the first part goes, we'll have negative 9 cos t equals 16 cos t sine t, cos t sine t. Then we can divide both sides by cos t like this, and from that we will have sine t equals, so we'll divide both sides by 16, negative 9 over 16. Now the question says we need to find the exact coordinates. Now if I just do the sine inverse of negative 9 over 16, I don't get an exact value. I get something like minus 0.597, like that. That's no good. I want the exact value. So is there an identity? Is there something that I can use to find the exact value? Yes, there is. I can use sine squared t plus cos squared t is 1. So if I rearrange that, I will get sine t equal to the square root of 1 minus cos squared t. And actually, if I do it the other way around, I really want cos t, don't I? So to find cos t, so let's just swap those around. So that will be cos t is 1 minus sine squared t. This will give me an exact value. So an exact value for cos t, and I want cos t actually, don't I? Because I can put that into the equation, is going to be square root of 1 minus negative 9 over 16 all squared. So what does that give me for cos t? Let's do that on a calculator and see. So now I get a nice exact value on my calculator as 5 root 7 over 16. Now I could actually have drawn a right angle triangle, call this angle here T, and then say, right, that's going to be 16, this side here is going to be 9, and then just used square root of 16 squared minus 9 squared, so this side will be 5 root 7. Yeah, and then that'd give me 5 root 7 over 16 for cos t, the exact value of cos t, and then use the cast diagram to check its sign, and that would be positive. So now I've got my value of cos t here and my value of sine t here. I can now use the general form of the equation of the line, because I've got AB. Let's write these down. So I've got A as 5, I've got B as 3, I've got sine t as negative 9 over 16, I've got cos t as 5 root 7 over 16, and because I want to find the exact coordinates where r cuts the x-axis, I've also got that y equals 0. So all of those can be substituted into here to work out x. So that's exactly what I'm going to do. So ax, so 5 x, so x is what I need to find, times by sine t, so that's minus 9 over 16, minus by, so b is 3, now y is 0, so everything else I'm going to write after this bit is going to be 0. So cos t is 5 root 7 over 16, so that's all 0 anyway, equals a squared minus b squared. Now a squared minus b squared, that is just 25 minus 9, that's going to be 16. So 16 cos t, which is this, 5 root 7 over 16, times by sine t, which is negative 9 over 16. So with a little bit of rearranging, I can find x. X is going to equal all of this stuff here, that's on the right hand side, the 5 root 7 over 16, times by negative 9 over 16, divided by 5 times by negative 9 over 16. So for x, and actually it works out to be exactly root 7, because that's going to cancel out, then the 5 is going to cancel out as well, and the 16, so the only thing that's left is root 7. So x is root 7, so the exact coordinate of the point is going to be root 7, 0 as our final answer. Okay, you should now be able to do exercise 3D on pages 77 to 78. The only thing that we've got to recap is the general form of a tangent or a normal to an ellipse. Okay, now as I said before, these are not in the formula book, so they will save some time. If you want to use them in the exam, you can just quote them, but remember, you could always just differentiate parametrically, use y1, y minus y1 equals mx minus x1 to find the gradient that way. So here are the results here. If you want to pause them and try to memorize them for ease of finding the equations of normal and tangents for ellipses. So let's just highlight this one here.